The critical values here, I'm going to call, because I don't actually have their value, I'm going to call theta 1 and theta 2, okay? So theta 1 will be this one, theta 1 will be in the second quadrant, and theta 2 will be the one that fell out in the fourth quadrant, all right? So that gives us our two critical values over this interval, and we also have the endpoints to worry about, 0 and 2 pi. Okay. So let's plug these back into the original function. Okay, the endpoints should not be too problematic. F of 0 equals 4 sine 0 minus 3 cos 0. All right, 4 sine 0 is nothing because sine 0 is nothing, and 3 cos 0 is 3, so I have negative 3. Putting in 2 pi will give us the exact same thing because these two functions are 2 pi periodic. So without doing too much calculating, we also get negative 3. All right. Now comes the difficult part, you might say. At least you may not have thought to do this doing it on your own. The difficult part is to plug these unknown theta values back into the original function to get how high or low the function value is there. So it'll be something like this. F of theta 1. All right, f of theta 1 is going to be 4 times sine theta 1. Right? Now sine theta 1, if I look over here, what would sine of theta 1 be? Well, sine is the opposite over the hypotenuse. That's why I got the hypoteni over here previously. So I'm going to get 4/5. Okay? So even though I don't know what theta is, the very fact that I know that theta causes tan to become negative 4/3 can help me to just draw a simple picture and figure out what sine and cos must be for that situation. Now, there are two situations, it's true. You got to be a little thoughtful about it. But we would have here minus 3 times cos theta 1. Cos theta 1 is going to be negative 3 on 5. All right, let's see what that adds up to. We have 16 plus 9 all over 5. So 25/5 is 5. Great. F of theta 2. Not all problems are as cumbersome as this. I chose it because of this difficult scenario. I wanted to demonstrate how to follow through with it. All right, so now we've got 4 sine of theta 2. So 4 sine theta 2, sine is going to be opposite over hypotenuse. Now it's negative 4/5 because we're in a different quadrant. Minus 3 times cos theta 2, right? Cos theta 2. Theta 2 is this time 3 on 5. Positive 3 on 5 as opposed to the negative it was a minute ago, again because of the quadrant switch. Now we have negative 16 minus 9. Negative 25 on 5 is negative 5. All right, so we see that the absolute max and min did not happen at the endpoints this time. It turns out what were local minimums and maximums turned out to be the absolute minimum and maximum on this particular closed interval, 0 to 2 pi. Okay? So we have our answer here. On this interval, there's no local, well, I guess there are local, there's still local, but the real concerning part is the absolute. The one absolute maxima, we found 1, and that is 5. So 5 here is the absolute max on this interval. It turns out that, again, this came from the derivative being 0. So in this particular context, this is also a local max. As well. Okay, even though they didn't tell us how to figure that out, we're assuming it because in these problems the critical values should be coincident with relative extrema because they said to find local extrema, even though they haven't given us a method to determine when a critical value is 1, so we should assume that all critical values at this moment are going to be coincident with relative extreme locations. So therefore, we'll also claim it's a local max, and absolute max on this interval for the number 5.